Read this? I can actually make that a little bigger. Can we read it now? 14 says a spherical balloon is inflated so that its volume is increasing at a rate of 3 cubic feet per minute. How fast is the diameter of the balloon increasing when the radius is 1 foot? Okay, fair enough. Right? How do I know it's a related rate? They always talk about how fast something is changing, right? And they give us rates. So that's one really big clue that it's a related rate problem. And so how do you approach it? Well, they're talking about a sphere. So instead of talking about a sphere, we need to review what the formula for a sphere is. I need to make sure I have enough room, right? So formula for a volume of a sphere is 4/3 pi r cubed. If you don't remember the formula for a volume of a sphere, don't worry. I did not remember the formula for a volume of a sphere until I took calculus because of these problems. In geometry, you may not have had to, I remember having to do a formula for a volume of a sphere in geometry, and that didn't stick with me until somehow in calculus you had to do these enough. I remember that. You're not going to have to remember the formula for the volume because even on the AP exam they give you the formula. All right. So, I did say I should draw a picture. I'm going to draw a picture. Here's our sphere. The problem with the sphere is there's not a whole lot of dimensions. You've got your ball and then you have a radius. So as far as drawing a picture of a sphere, usually pictures are helpful. Spheres, not so much. All right. So, how do we do when we do related rate problems? We need a chart. What letters are in my chart?
R.
And what are the only letters I've got on the board? R and V. So I'll put V, I'll put R, and because this is calculus, I'm going to have dV dt and dr dt. Okay? So what do we know?
Radius is 1 foot.
Radius is 1 foot. What else do we know?
dV dt is 3 feet per minute.
We know dV dt is 3 cubic feet per minute. What are we looking for?
2 dr dt.
I want to talk about that in just a second. Does everybody see we're looking for the rate that the diameter is changing? It's asking for the rate that the diameter is changing. You are absolutely right, it is 2 dr dt, but I don't want to talk about why. You're doing it conceptually, which is perfect, but I also want to talk. So if I have d and then dd dt, right? I have my diameter and then the rate that the diameter is changing. This is what we're looking for. Right? We're looking for the rate that the diameter is changing, and we're going to address that in a little bit. Right? But could I find out what? Let's just look at what I have written in blue. And what I have written in blue is I have dV dt, I have r. I want to find out. I need to find out dr dt because that kind of looks, based on what it's giving me, it looks like I could fill this out. I do need to talk about these questions that involve volume. You always need dV dt. V you never need. So when we talk about volume, and I am going to talk about volumes of spheres, cones, cylinders, you never need this as far as the calculus part. So the fact that we don't fill this out is fine. Right? All right. So I've gotten all my information. I need some room to write, so I'm going to minimize this. So what do I need to do? Right? So at this point, what can I do? If I wanted, do I have an equation that relates V and R? What's the equation that relates V and R?
V equals 4/3 pi r.
My volume thing, right? So I have this equation that's V is equal to 4/3 pi r cubed. I need something that has dV dt and dr dt. Right? Since I need something that has dV dt, I need something that has these values, right? So I've got an equation that relates V and R. I need to take the derivative. Curious, do I need to use product rule?
No.
Why?
don't
These are
need-
just constants.
Yeah.
All right? Anytime you have constants multiplied times something, this is just like decoration. So when you take the derivative, like when I take the derivative of this side, that's going to give me dv dt equals, this is decoration, so I'll just go ahead and write that down as 4/3 pi. And what's the derivative of this? 3r squared dr dt. Now you may not, it doesn't seem that important in this problem, but it will in the next one. Once you take the derivative, you want to clean it up. The cleanup is going to make your life so much easier. See how the 3's cancel? So if I look at this, I end up with dv dt is equal to 4 pi r squared dr dt. And do I have enough information so that I can figure out what dr dt is? What do I do? Just plug in the stuff, right? Let's see, dv dt is 3. So I get 3 equals 4 pi, r is 1, so that's 1 squared, dr dt. So I end up with dr dt is equal to 3/4 pi. That's going to give me 3/4 pi, which is great, fine. I figured out the rate that the radius is changing. But the question didn't ask that, right? The question, the problem said, how fast does the diameter change? Okay. Is there a relationship between the radius and the diameter? Yeah, there it is, right? It's diameter is equal to 2r, isn't it? Well, that's an equation. Any equation you can write down, you can take the derivative of both sides. If I take the derivative of both sides, what do I find out? dA dt equals 2 dr dt, right? Well, if dr dt is 3/4 pi, what's the rate that the diameter is changing? 2 times that, right? So this is going to be 2 times 3/4 pi, which simplifies to 3/2 pi. Oh, that's not going to be feet per minute. Notice this is a volume, so it's cubic feet per minute, and this is a length, and so it's just 3/2 pi feet per minute. That kind of makes sense. Okay, so as far as the geometry problems go, you got a volume. Whenever you write your formula down, go ahead and put all the letters down and d something dt. Don't worry that you don't know what the volume is. You never do. Right? But you need to know about the dv dt. Plug stuff in. It's nice if they say what's the rate that the radius is changing, because that's part of sort of the way we're part of our setup. But sometimes they'll say, well, what's the diameter doing? And you say, well, sometimes you have to write another equation. Or you could think about it. Think about a ball. If the radius is increasing at a certain rate, are we okay? And you can think about the diameter. Think about the diameter of a ball as basically being 2 radii. So if this radius is increasing at this rate and this radius is increasing at that rate, do you see that the diameter is going to be increasing at twice that? Because it's going in 2 different directions. Right? So how did this one, did this kind of make sense? The picture, drawing a sphere, yeah, not a big deal, right? That one is not as helpful. All right, so this next problem, dang it. I didn't talk as much and I'm still almost out of time. Okay. So every calculus book I've ever taught out of, we're going to do problem 25. If you had to pick like the most important, or not the most important, but probably the most common related rate problem, it's going to be a cone problem, right? In fact, a lot of times when I teach this, I call it the famous cone problem, right? This is, if your parents took calculus in college and you said related rate cone problem, they're going to go, Oh yeah, I remember that. And it could be 30 years ago, right? It's just that common of a problem. There is always a cone problem in a calculus class. We are a calculus class, therefore we will have a cone problem, right? So here is our cone problem, right? So first thing I'm going to do is read the problem. It says a conical water tank with vertex down has radius of 10 feet at the top and it's 24 feet high. If water flows into the tank at a rate of 20 cubic feet per minute, how fast is the depth of the water increasing when the water is 16 feet deep? All right, I need to draw a picture. So here's my cone. All right. Do that. Let's see, the radius of the cone is 10. The height of that cone is 24. And we have water. Right? Like there's water in the cone, right? Notice I put numbers for the dimensions of the actual tank because the tank doesn't change. So I can put numbers. But that water level, because water's being poured in, are we okay that the water level is changing? Yes. And since the water level is changing, the radius of the water level is changing and the height of the water level is changing. And what we need next, since we're talking about a cone, I need the volume of a cone. And the volume of the cone is 1/3 pi r squared h. All right. I've drawn my picture, right? I've got my formula. What letters are going in my chart?
R, H.
V, R, and H. Is everybody okay with that? So I've got V, I've got R, I've got H. Yeah. And since this is calculus, I have dV dt, I have dr dt, and I have dH dt. I didn't put an equals by the V because we never use it. All right, now let's read the problem and figure out what we know in the chart and what we're looking for. What do we know?
A radius of 10 feet.
Oh, no, that's the radius of the whole tank, right? What do we know about the water? Notice I put it in blue because I'm talking about the water.
dVdt is 20.
What?
The dVdt is 20.
Okay, so this is 20. Is it positive or negative?
Positive.
Why?
Because it's filling up.
Because it's filling, it's adding, right? Sometimes they have these problems where the water's leaking, so your dVdt is negative.
16.
What?
H is 16.
H is 16. What are we looking for?
The dH dt.
What's the rate that the depth's changing, right? So we're looking for dH dt. Ah, perfect. Is everybody okay with my chart? Okay, we've gotten all the information and I need the board space, so we're going to minimize this. All right. Well, if I treat this problem just like I treated if I treat this problem just like I did the sphere problem, I guess I'll write my volume equals 1/3 pi r squared h. And I've got a few issues here. One, I don't have any information about r, do I?
You can solve for r and then plug it
Yeah,
in.
you can find it. Okay, yeah, we could. We could figure out r. And I'll talk about how we could do that. So that's one problem, right? I've got to figure out r. The other problem is I'm going to have to take the derivative of this, right? Because that's how these work.
We have three
You're going to have to take the derivative, and what am I going to have to use?
particles.
Yeah, everybody see I have to use product rule because I have two letters multiplied together? I don't want to.
And you substitute
Okay.
now.
I really don't want to. And the reason that we always have cone problems in this section is you don't have to. Right? I'm going to talk about the method of wishful thinking. My method of wishful thinking is, wouldn't it be nice if I only had one letter over here? instead of R's and H's?
Yeah.
If you could pick one letter, which letter would you pick?
R, probably H.
Well, what are you looking for?
DHDT, so.
If you're looking for DHDT, wouldn't it be nice if this was all H's?
Yeah.
Because if it's all H's, it's easy, right? You just take the derivative, plug stuff in, you're fine. You don't even have to worry about the product rule, right? So we'd really like H's. Now, the reason cone problems exist in every single calculus book is there's a way that you can change all your R's to H's. And here's how. Use similar triangles. What I'm going to do, can you see like there's two right triangles? We've got the tank, which is this thing, where it's 10 and this is 24. And then we have the water, which is this thing, which is R and H. And they're similar triangles. Okay? And since they're similar triangles, can you give me a proportion?
10 to 24.
Proportion is an equation.
Uh,
What does 10 over 24 equal?
R of H.
Did everybody get that? So if I look at this, I can say 10 over 24 is equal to R over H. Well, whoops. How about I try to actually make that neat? Now, wait, what letter do we want here?
H.
I want H's, right? Since I want H's, I need to change R into something. So if I solve, can you see that R is going to equal, and I'll go ahead and make that 5 over 12 H. See what this does is this converts all my R's to H's.
Yeah.
It says everywhere you see an R, write 5 over 12H. Well, I can do that. So I'm going to rewrite this and say V is equal to 1/3 pi, but instead of R, I'm going to write 5 over 12H squared times H. Now, very, very important step. Clean this up. The biggest mistake students make when doing a cone problem or something similar to this is they do this work and they try to take the derivative of this rather than do a little cleanup. See, a little cleanup goes a long way. If I look at this, that's going to give me V is equal to 1/3 pi, so that's 25 over 144 H squared times H, which is equal to 25 pi over, I'm going to say that's 3 times 144, because we don't actually need to multiply it out, H cubed, and I get V. So I've cleaned it up. Yay. Now what? Take the derivative. This is almost like our sphere problem at this point. That's just some number, isn't it?
Mm-hmm.
That's some number that's decoration. And so when I take the derivative of this, I end up with dv dt is equal to, there's my number, so I get 25 pi over 3 times 144. And the derivative of h cubed is going to give me what? 3h squared dh dt. Yeah, then the 3's cancel. Start over here, so I end up with dv dt is equal to 25 pi over 144. Okay. What was h?
16.
16. And so let's see, we get dv dt is equal to 25 pi over 144, 16, let's see, so that's 256 times dh dt, and let's see, 16 goes into 256 16 times, and 16 goes into this 9 times. The rest of this is just arithmetic. Oh. Oh, shoot. Oh, I forgot to plug in dVdt. And
Oh, yeah.
here, I'm going to start over. If I plug in dVdt, which is 20, and that's 16, right, all I did was clean this up. Now I'm plugging what I know. I'm looking for dHdt. The rest of this is arithmetic. So let's see, that's going to give me 20 is equal to 116 goes into that 9 times, so I end up with 25 pi over 9 dHdt. And if I want to solve for dHdt, I'm going to multiply both sides by, oh, there's another 16. I'm out of room. All right, so arithmetic. This is 20 is equal to 400 pi over 9 dHdt. So, we took the derivative, then we plugged stuff in, and then the rest of this is number sense. Use a calculator, right? Multiply, and now to solve for dHdt, I'm going to multiply both sides. Multiply by 9 over 400 pi. That's 9 over 400 pi. So this is gone, and 20 goes into that 20 times, so I end up with 9 over 20 pi is equal to dHdt. And so this is going to give me 9 over 20 pi. What are my units?
It's gonna be.
Is it a length, an area, or a volume?
Length of feet per minute.
So this is going to be feet per minute. Now, I want to recap what we did, because I'm actually a little worried that some people may have felt overloaded when all I was really doing is multiplying and dividing in my head. We started with a cone, right? We write the formula for a volume of a cone, we write stuff down. Okay? We had some issues, like we knew we were going to have to take the derivative of this. The problem with taking the derivative of this is we're going to have to use product rule, and that's fine, except I don't even know what R is. And the reason that the reason that calculus books have cone problems is anytime you have a cone, you have a similar triangles, and so there's a relationship between R and H. And you use that relationship between R and H that I had to erase to get a volume equation that only has one variable. Then the derivative of this is actually pretty easy. You got some ugly number times 3h squared dHdt. And then once you get to this stage, you can just plug what you know. You know dVdt, you know h, and you're looking for dHdt. So you clean this up a little bit, and then solve, and we get 9 over 20 pi, and you have to remember the units because the AP exam is concerned about units. All right, your homework. I have given you a handful of related rate problems. I need you to attempt them. There's a cone problem. There's another, I think there's one other, there may be one or two more right triangle problems. I think there's a sphere problem. But tomorrow,